So why do we care about the squeeze theorem? Because the squeeze theorem can prove multiple theorems for us. In particular, it can prove the following three theorems that are very important to us. The first being the limit as x approaches 0 of sine of x over x is 1. The second one being the limit as x approaches 0 of 1 minus cosine of x over x is 0. And the third one, which is the limit as x approaches 0 of 1 plus x all over to the 1 over x equals E. So that's another definition of E there for you, by the way, but really cool. So the squeeze theorem was used in the proof of all three of these. You can see that in the textbooks if you want. It is in the appendix section, and it's actually proven in the book as well. So really cool there for you to see if you want to see the proofs of those, but the squeeze theorem is what is used to prove those. Okay. These I do not expect you to be able to prove. I do not expect you to do anything but memorize them. If you're allowed a note card, I'm not going to lie, these would be on my note card without a doubt. So let's go ahead and see them in action. Sometimes the application of these theorems might not be quite so easy for you to see. So for instance, it says, what's the limit as x approaches 0 of tangent of x over x? Well, my good old go-to is, this is a fraction, and both of these are functions I can plug it into. So let's try plugging it in. And if I plug it in, I'd have tangent of 0 over 0, which would be 0 over 0, which is undefined, or sorry, more so I should say indeterminate form instead of undefined. It is undefined because you're division by 0, but it's that indeterminate form. Again, that does not mean the limit doesn't exist. That merely means we cannot just plug in 0 to get the limit. So we have to do something else. Well, what this does is this makes me think about what is tangent of x. And if you remember, tangent of x is really sine of x over cosine of x. All of that would be over x, but what I'm really going to do is write it as x over 1. So really what I have here is a compound fraction, a fraction over a fraction. And if you remember what to do with that, you keep the top fraction, you flip the bottom fraction, and you change it to multiplication. So this is the same thing as the limit as x approaches 0 of sine of x over cosine of x times 1 over x. Well, isn't this the exact same thing as the limit as x approaches 0 of sine of x over x times 1 over cosine of x? Okay, what did I do there? All I did was swap the order. Remember, multiplication is commutative. 2 times 3 is the same thing as 3 times 2. So cosine of x times x is the exact same thing as x times cosine of x. So all I'm doing is kind of thinking about these, changing the orders of these because we can do this. Why do I care about that? Because what I'm able to do is this is a limit of a product. Well, that's the limit of the product of the limits, right? So this is the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. And this is one of the special limits that we know here. We know that the limit as x approaches 0 of sine x over x goes to a value of 1. And the limit as x approaches 1 over cosine of x, well, you'd plug in a 0, you'd be finding the cosine of 0, and if you evaluate the cosine of 0, this is also a 1. So what am I getting? For the first one, I'm getting a 1. For the second one, I'm getting 1 over 1, which is just 1. So I'm getting a limit total of 1. So what's the limit as x approaches 0 of tangent x over x? The answer is 1. Again, I wanted you to solve for this analytically or algebraically, but we could always verify using a table here. So try going onto your table, plugging in tangent x over x, plug in values just to the left of 0 and just to the right of the 0, and you should see those numbers approach 1. Let's continue going on with some more examples. How about this one? Another great example that I see on tests all the time from different calculus teachers. It says, find the limit as x approaches 0 of sine of 4x all over x. Well, what's the issue here? Here's what the real issue is. Well, let's start how we always start. Sorry, I don't want to get ahead of myself. Start how we always start. Start by plugging in 0. So this would be 4 times 0, which is 0 all over 0, right? So this is sine of 0 over 0. Well, sine of 0 is 0. So this is 0 over 0, which is our indeterminate form. So we know that we can't just plug in the limit. It means we need to do something else. Well, here's the rule right here that I'm talking about. if you notice, here we have a 4x, sine of 4x, but in the denominator we have an x. Those two things don't match. And in order for you to use the rule, which is the limit as x approaches 0 of sine of x over x, those two things need to match. So if they don't match, what can we do? I mean, here's what I'm getting at. Here's what I really wish we saw. If we had the limit as x approaches 0 of sine of 4x over 4x, because those two things match, we know that approaches the value 1, but those two things have to match. Well, they don't. So what could we do to make them match? Well, do you agree that I can multiply something by 4 over 4? I mean, isn't this the same thing as the limit as x approaches 0 of sine of 4x all over x times 4 over 4? I mean, isn't that technically true? Because that's just multiplying by 1. Well, what am I going to do now? Now I'm just going to be a little creative here. I'm going to say this is the limit as x approaches 0 of sine of 4x all over. Well, I am going to multiply out the bottom. That's 4x, but then I still have that times 4, right? Well, what am I able to do with those constant multiples? I'm able to pull those out in front, aren't I? So isn't this 4 times the limit as x approaches 0 of sine of 4x all over 4x? And now I can use my rule because the sine of 4x matches the 4x on the bottom. Now I know that approaches the value of 1. So this would be 4 times 1, which is 4. Our final answer for the problem. Okay. So great problems that you see there, just a little bit of manipulation. We've learned some wonderful rules this section. We learned if it's a polynomial, a rational, one of our radicals, one of our transcendental functions, which is our 6 trig functions, our exponential functions, our logarithmic functions. To evaluate a limit, simply plug it in, as long as you can do it. We're going to run into cases where you can't plug it in, where you're going to factor and simplify first. That's on the test. You're going to run into an example where you have radicals and you have to rationalize the numerator or denominator. That's on the test. And then we're also going to have examples like this where you can't factor and simplify. You can't rationalize the denominator. You need to use one of the tricks. One of the tricks being one of these 3 theorems right here. The limit as x approaches 0 of sine of x all over x equals 1. The limit as x approaches 0 of 1 minus cosine of x all over x equals 0. Or the limit as x approaches 0 of 1 plus x all raised to the 1 over x is equal to e. So without a doubt, I'm thinking right here, at least 4 problems on the test. One where you can plug it in, one where you have to factor and simplify first, one where you're dealing with rationalizing the numerator or bottom denominator, and one where you're using one of these rules. That's at least 4 problems on the test right there.